Now we're going to look at partial fraction expansion. Partial fraction expansion is used when we want to simplify a rational expression into a sum of simpler rational expressions. So first of all, what's a rational expression? A rational expression is just a fraction where there's a polynomial on the top and the bottom. So you'd have a polynomial expression on the top divided by another polynomial. So this could look something like s plus 2 times s plus 4 divided by s cubed plus 4s squared plus 3s. So that would be a rational expression. In this course, we're going to use partial fraction expansion to simplify expressions in order to integrate them. There's actually a lot of applications for partial fraction expansion. You're going to be using this up until your final course in your energy program, so it's worth understanding well. And just a quick note that the numerator must be lower than the denominator. Lower order. I've got the word here. Lower order. So that means, for example, in the example that I put up here, this is a second order equation, and this is a third order equation. So just make sure that the numerator is of a lower order than the denominator. So there's three cases of partial fraction expansion that we'll deal with in this course. The first one is if you have distinct real roots. The second one is if you have repeated real roots. And the third one is if you have complex roots. So let's go through each one, and I'll do an example for each one. And I'm actually going to use the example from up here for the first one. So I'm going to move the screen up. The first case is distinct real roots. So I'll rewrite the fraction. So let's say we have y of s is equal to s plus 2 times s plus 4 divided by s cubed plus 4s squared plus 3s. The first thing that you need to notice here is to be able to see that this expression on the denominator can be expanded, can be factored out. So this is equal to s plus 2 times s plus 4 divided by s times s plus 1 times s plus 3. So what we've done here is we've now identified the three roots of our equation. From here, to do partial fraction expansion, what we're saying that this expression here can be expressed as a sum of individual fractions. So when you do partial fraction expansion, you're saying this is equal to some constant over s plus some other unknown constant over s plus 1 plus some other constant c3 over s plus 3. And so each root here becomes a denominator, that's misleading, becomes one of the denominators here. And then your job is to figure out and identify what the value of these constants would be. I'm going to show you the cover-up method. This is a really simple way of doing this. And so what you do is, let's say you're looking for C1, you're looking for C1. You rewrite the full polynomial, the full rational expression, and you cover up the denominator that relates to C1. So you say C1 is equal to, and I'll write the whole thing up. So you have s plus 2, I forgot a bracket up here, times s plus 4 divided by s times s plus 1 times s plus 3. But then you remove the denominator related to the coefficient you're looking for. And then you evaluate this as s is going towards the value of that denominator. So in this case, the root of that denominator. So in this case, s is going towards 0. So when you evaluate this, you have the s's all go to 0. So you have 2 times 4 divided by 1 times 3, which gives you 8 divided by 3. That's your coefficient for C1. C2, you do the same process, so you have s plus 2 times s plus 4 divided by, this time I won't write it in, but you have s times s plus 3. So what's missing is the denominator related to C2, which was s plus 1. You evaluate this as s goes towards minus 1. So whatever would set the denominator of C2 to 0 is what your s is veering towards. Or it's not veering, it's not the limit, it's actually, you're just setting it equal to. So let's be a little bit more clear here. It's actually just equal to whatever would set the denominator to 0. So then this becomes 2 times 4 divided by negative 1 times negative 1 plus 3, which is equal to negative 3 over 2. For C3, same process, s plus 2 times s plus 4. This time it's s times s plus 1 on the denominator, and s is equal to negative 3. And now this will be equal to negative 1 over 6. Now when you rewrite your equation, you have y of s is equal to 8 over 3 divided by s plus negative 3 over 2 divided by s plus 1 plus negative 1 over 6 divided by s plus 3. And now you've rewritten your equation in terms of 3 separate rational functions that are much easier to deal with. The next method that we're going to do is the repeated roots example. And this is it's a very similar process, but what happens in this one, I'm going to move the screen all the way up. In this one, when you have repeated roots, this means your equation looks something like this. You have f of s is equal to s plus 3 divided by s plus 2 squared times s plus 1. In this case, this root here is repeated, and you have to do a slightly different method. So instead of saying, if we were following the same rules as the method before, we would say C1 plus over S plus 2 plus C2 over S plus 2 plus C3 over S plus 1. That's not quite correct. When you have repeated roots, you raise one of the denominators by the expression here of the number of times it's repeated. So here you would have S plus 2 squared as one denominator, and then here you would have S plus 2 to the power 1, and then you would have your other root. Let's say, for example, you had S plus 3 divided S plus 2 to the power of 3 times S plus 1. Then you would have C1 over S plus 2 cubed plus C2 over S plus 2 squared plus C3 over S plus 2 plus C4 over S plus 1. So you can see the pattern there. So it's important with repeated roots that you don't follow exactly the same method as the video before. Now from here, there's different ways of solving it. For C1 and C3, we can use exactly the same method as before. So C1 would be equal to S plus 3 divided by, now this is very important. Here, you make sure that you're using this denominator and then removing the term under the coefficient that you're looking for. Don't use these three combined. So here you have S plus 2 squared times S plus 1, and you remove the denominator under the C1, so that means we remove this denominator and we evaluate at S equals minus 2. This gives us minus 2 plus 3 divided by minus 2 plus 1, which gives us minus 1. For C3, we have S plus 3 divided by S plus 2 squared, evaluated at S equals minus 1. Same method as before. This is equal to minus 1 plus 3 divided by minus 1 plus 2 squared. This gives us 2. For C2, to solve for C2, can you see where we might run into trouble? Because for C2, if I had to use the same method, we have C2 is equal to s plus 3 divided by s plus 2 squared plus s plus 1, times s plus 1. If I remove the denominator related to C3, that means I'm just removing that coefficient, so we just have 1s plus 2. When I evaluate this at s equals minus 2, I'm going to end up with minus 2 plus 3 divided by minus 2 plus 2 times minus 2 plus 1. This right here is equal to 0, and you can't divide by 0. So this method will not work for C2. But what does work is a little trick, is you take the derivative. So you take C2 is equal to the derivative with respect to s, and now you multiply the function f of s by the repeated root. So in this case, it would be s plus 2 squared times f of s, evaluated at s equals minus 2. So this looks complicated, but it's not too bad. So this is equal to the derivative with respect to s of s plus 2 squared times our function, which was s plus 3 divided s plus 2 squared times s plus 1. These will always cancel out. And now you just have to take the derivative of s plus 3 divided by s plus 1. That's really straightforward. I'll write out the steps. You end up with 1 times s plus 1 to the negative 1 plus negative 1 times s plus 1 to the negative 2 times s plus 3. So here I use the product rule even though it's a derivative. And then, then you evaluate this at s equals minus 2. This gives you minus 2. So then our final function here, f of s, is equal to negative 1 over s plus 2 squared minus 2 over s plus 1 plus 2 over s plus 1. This is over s plus 2. And that's our simplified function. I'm out of time in this video to go through the third method, so that'll be in the next video.